Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up our work with the normal distribution that we've been doing now for a couple lectures. In the past couple lectures, we studied what the normal distribution is as a theoretical distribution. We learned some important facts about the normal distribution, such as the fact that it's a perfectly symmetric bell shape that is a two-parameter distribution based entirely on the mean and standard deviation. We also learned the empirical rule, which basically said that if we had a normal distribution, then no matter what the distribution is in terms of what type of data we're looking at, as long as it's normally distributed, we know 68% of the data should land within one standard deviation of the mean, 95% of the data should land within two standard deviations of the mean, and 99.7% of the data should land within three standard deviations of the mean. We also saw from the empirical rule that in general, when working with a normal distribution, if we can understand the relative position of a data point relative to the mean based on the standard deviation, aka the z-score of a data point, we can get a tremendous amount of information about the population, the percentage of the population above that value, below that value, between two values. We can also sort of work backwards. We can take an individual's percentile rank and convert it into their most likely value for for whatever variables under study. So we've done a lot with the normal distribution. However, for our work so far with the normal distribution, we've applied it from a mostly theoretical perspective. And what we mean by that is that we've sort of assumed that we had knowledge of a full population that we were told was normally distributed, and then we were able to sort of draw these interesting conclusions, right? And so every problem sort of started off with assume the population is normally distributed, here's its mean, here's its standard deviation, go from there. What we'd like to investigate now, though, is if these conclusions apply to actual data sets, maybe only samples, and maybe these samples aren't going to be this perfectly smooth bell curve, but they're only going to be roughly normally distributed. As we will see in the next couple of examples, the predictions from our theoretical work, we're going to focus basically on the empirical rule, will turn out to be quite accurate even when the data is only approximately normally distributed. So we're going to sort of get back to actually having data sets and samples, and we're going to see that this stuff that we're doing with the normal distribution, even though it sort of assumes a perfectly smooth bell curve, well, in real life, we're not going to have a perfectly smooth bell curve, but the actual conclusions that we get from all of our work we've done so far really do apply even to real data sets. So let's go ahead and jump right into these examples here. So for our first example, we're going to suppose that we have a researcher that's studying the reaction time for adults. So to study this, the researcher gets a group of 15 volunteers to take a reaction test where they have to respond to a visual stimuli. Then the researcher records their reaction time in milliseconds. So we get this data set here. So we can see somebody reacted in 230 milliseconds. Somebody took, say, 261. Somebody was all the way as long as 284. So we're going to do a bunch of stuff with this. First, because this is back to just being an actual data set, we're going to calculate some basic measures, mean, median, and standard deviation. Then we're going to construct a stem plot and try to describe the shape of this data. And then in parts sort of C through G, we're going to start to talk about the empirical rule. We're going to decide, is it really appropriate to apply the empirical rule to this data set? And then we're going to take a look at a couple of things that the empirical rule would predict and how accurate those predictions actually are. So let's start off with getting the mean, median, and standard deviation for this data set. So what we'll need to do here is we'll need to take this data and pop it into our calculator. So we'll take all of this stuff here. And of course, it doesn't matter what list you're going to put it into, but I'll just pop it into L1. So if we hit Stat and Edit and clear out any data that might be in there, and then start to put this in 230, 246, 247, 250, 252, 254, 255, 258, 261, 263, 266, 268, 273, 277, and 284. And we can check when you're on 284, it should say like L1 of 15, indicating we did type in 15 data points, which we know we were supposed to because our sample were those 15 volunteers. Then we can hit Stat, Calc, and 1var stats, and go ahead and calculate this stuff here, and we want the mean, median, and standard deviation. So it looks like the mean here should be approximately, we'll keep one decimal place since the numbers are pretty large, 258.9. And of course that would be in milliseconds because all the data points were in milliseconds. The median, if we scroll down a little bit, should be 258 milliseconds. And the standard deviation, where we would want to use the sample standard deviation, of course, because this is a sample, it's only 15 people. If we round to one decimal place as well, looks like it should be 13.7 milliseconds. All right, what do we notice right off the bat? Well, we notice that the mean and median are very close to each other, 258.9 and 258. What that indicates is that the distribution for this data set is most likely a symmetric distribution. It shouldn't be left or right skewed because the mean and median are very similar. Does this mean that it's guaranteed to be Bell normal? Not necessarily, right? In fact, in our class, we talked about two different symmetric distributions, Bell normal and uniform. So, unfortunately, by seeing that the mean and median are roughly the same, it doesn't tell us which of those two symmetric distributions it actually is going to follow. So, we need to construct a stem plot and use that to describe the shape of the data. So, if we look at our data, we have 3-digit numbers here, and the last digit actually does matter, so we'll use the last digit as the leaf, and we'll use the first two as the stem. So it looks like we'll have stems of 23 all the way up to 28. So no need to do a split stem plot here. So we'll have 23, 24, 25, 26, 27, and 28. And we'll go ahead and draw it. Looks like for the 23, we have that 230. For the 24s, we have that 6 and 7. For the 25, we have 0, 2, 4, 5, and 8. So 0, 2, 4, 5, and 8. For the 26, looks like we have 1, 3, 6, and 8. So 1, 3, 6, and 8. 1, 3, 6, 8. For the 7s, we have 3 and 7. So 3 and 7. And then for the 28s, we have just that 4 there. So there we go. There's our stem and leaf plot. We can include a key below it. 23/0, for example, is 230 milliseconds. All right, what sort of shape are we seeing here? Well, if you want, you can sort of draw this in, though we can probably already sort of tell what this looks like. Right, we're going to describe it as anything. It looks like there's sort of a tail this way, a tail this way. We probably would go ahead and describe this as roughly Bell normal. Now, is it a perfectly smooth bell? Definitely not. It seems like the sort of peak is right here, and there is a longer tail out to the right than there is to the left, but there's tails in both directions. It wouldn't really make sense to call it anything else. So if we're picking one of the 4 distributions we have for our class, we'd say this thing is roughly Bell normal. Okay, now we want to understand, would it be appropriate to apply the empirical rule to this data set? Well, you might say, can't we always just use the empirical rule? Well, remember, the empirical rule only applies to normally distributed data. So if you just have a random data set, you can't necessarily apply the empirical rule. But we just did this visual display here, and we've now confirmed that it's roughly Bell normal. So our answer to C here would be yes. We can apply empirical rule since data is roughly normal. If the data followed a right skew or a left skew or looked uniform, then we wouldn't be able to apply the empirical rule. But since the data is roughly normal, we can definitely go ahead and apply it. Let's go ahead and apply it on the next page then. So this will be for part D here. So for part D, we said according to the empirical rule, which we now know is appropriate to use, between what 2 values should 68% of the data land? Well, if we think back, right, empirical rule, 68% of the data should land in, well, we know that for the empirical rule, 68% of the data should land within 1 standard deviation of the mean, meaning 1 standard deviation below the mean to 1 standard deviation above the mean. Now, in the past, we always wrote that as like mu minus sigma, mu plus sigma, because we were dealing with populations. That doesn't quite make sense here because we have a sample. So instead we would say the mean minus the standard deviation, x bar minus s, up to x bar plus s. So 68% of the data should land in here. Can we actually say what those values are? For sure, we calculated those, right? We know that the mean is 258.9 and the standard deviation is 13.7. So let's go ahead and put that in there. 258.9 minus 13.7, 258.9 plus 13.7. So there we go. We've got our sort of values there. We can go ahead and actually figure out what those look like. So let's go ahead and do our subtraction first to get the low end, 258.9 minus 13.7. The low end would be 245.2. 258.9 plus 13.7 would be 272.6. So 68% of the data should land in this interval from 245.2 up to 272.6. Okay. Notice that this would be a prediction. It's a prediction according to this theoretical rule, the empirical rule. We confirmed that it's appropriate to use it because it's normally distributed, but this is just a prediction. All right, let's see how accurate the prediction actually is. So in part E, we're going to say what percent of our sample actually lands in this interval. So in other words, what percentage of the sample actually is in this range that's supposed to catch 68%? Well, if we think about that, let's think about this interval sort of in red here. So the low end is 245.2. So if we go over here, right, 245.2 would catch everything from here. So it would catch the 246 and onwards because it'd be 245.2. It would go all the way up to 272.6. So 272.6 would end right about there. Right? It would catch the 268, but not the 273 because that would be outside the 272.6. So how many data points is that? Well, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's 11 of the data points. Out of how many? Well, we had 15 volunteers, so 15 data points. So what actually landed in that range was 11 out of 15. If we do that division, we can see that that comes out as approximately 73.3%. So what we can see there is that while the empirical rule said that 68% of the data should be in there, in our data set, it's a little different. It's 73.3. It's a little bit higher of a percentage of the data that lands in this interval. But notice this 73.3 is close to that 68, right? And again, it's not a perfect value. It's, predicted to be 68. It actually is 73.3. But keep in mind, our data set was not perfectly normal. It was only roughly bell-shaped or normal. And you can see that even in this situation where it was sort of only roughly bell normal, the prediction is relatively close to what actually happens. All right, let's try this again. Let's take this a little bit of a step further, and let's look at the empirical rule for 95% of the data. So for part F here, if we want to do the empirical rule, and we have 95% of the data should land in what interval? Well, for 95% in terms of the empirical rule, we know that's within 2 standard deviations. So we do x bar minus 2s all the way up to x bar plus 2s. So let's go ahead and calculate that. That's going to be our mean was 258.9 minus 2 times 13.7 all the way up to 258.9 plus 2 times 13.7. All right, we can calculate those. Just directly type each one into your calculator. So 258.9 minus 2 times 13.7. The low end should be 231.5. And 258.9 plus 2 times 13.7. The high end should be 286.3. So there we go. 95% of the data should land in this interval, 231.5 up to 286.3. All right, let's see how much of the data actually lands in that interval. So this time to sort of delineate it, we'll go ahead and do this in blue. So 231.5 Well, if we think about that, 231.5 is going to catch everything over here except for the 230. The 230 is too low. And the 286.3 is going to catch all the way up to here. So in other words, all of the data points except for that 230 are going to be in that range. Well, that would mean that there's 14 out of the 15 data points. For G, we'd say 14 out of 15. And if we write that as a percentage, 14 divided by 15, you'll see that that comes in as 93.3%. So the empirical rule says that 95% of the data should land in there. For our data set, it's only 93.3%. But notice that's very close, right? What we would sort of expect, according to the empirical rule, is 95%. What actually happens, 93.3. Again, that's a pretty good level of accuracy, especially considering that our data set was only 15 data points. That was only roughly normal. So again, part of this is trying to do a little bit of review about things like what are the basic measures, how do we visualize data, but part of it is also showing you guys that it actually is sort of worth learning from a theoretical perspective how to work with normally distributed data, because even with things that are only roughly normal, the predictions from that theoretical work really are pretty accurate. Okay, well, let's go ahead and try this one more time with another data set. So we'll get back to really talking about sort of all the things we've discussed so far with quantitative variables as well as the normal distribution. Let's suppose that we've got a public official for a small town in California that wants to study the monthly electricity used by households in their city. So to study this, the researcher randomly selects 3 blocks from the city and samples all the households on those blocks. The official ultimately gathers data about 24 households. So for each household, the official records the electricity used in the last month. Normally, electricity used is measured in kilowatt hours, so that's how they measure that here. And they get the following data. So one household used 310 kilowatt hours. One house used all the way up to 515 kilowatt hours. So we're going to do a tremendous amount of stuff with this. A couple sort of basic terminology things from way back earlier in our class. Population, sample, and individual. Sampling technique. Basic statistical measures, mean, median, standard deviation. Another visual display, a histogram. Then we'll get to talking about whether or not the empirical rule is appropriate for this data set, and then we'll make some predictions and see how accurate those predictions are based on the empirical rule. So let's go ahead and see. Oh, I noticed a little typo down here. Let's just go ahead and get rid of that. This should be F, and this should be H. Right. Sorry about that. Okay, let's go ahead and take a look. So first, we want to start with population, sample, and individual. So let's think about what we have here. We can sort of see that they gather data about 24 households. So we know our sample should be 24 households. So notice that this time the sample is not an amount of people. In this case, it's an amount of households. That means an individual here is actually one household. Not one person, but one household. How much does one household use in terms of electricity? And the population, well, in our standard structure, it should be all households in this city, right? Because they're only interested, or this official is only interested in studying the households in this town. So we can say that the population is all households in the city. Notice there's no mention in any of these of the variable, which is the amount of electricity used. That is the variable, so it does not appear in the description of the population, sample, or individual. For B, we want to know the technique that was used here. Well, we can see that it mentions right in there that they did this randomly, so that narrows down our choices. Remember, overall, we have 5 choices. We've got SRS, systematic, stratified, cluster, and convenience. By seeing that word randomly mentioned in there, we know that that means it either has to be an SRS, a stratified, or a cluster. Notice that in this situation, the amount of selections was 3. They selected 3 blocks, and they sampled all the households on those blocks. So while the researcher only made 3 selections, they ended up with 24 data points. Anytime the number of selections doesn't match the number of data points, you know that every selection was actually a cluster. So this would be a cluster sample here. So this would be a cluster sample, and the clusters were each block. Each block had multiple households on it, right? And if you just think about like the block that you might live on, right, there's probably multiple houses or multiple households on that single block. When you select one city block, you get several households. That's why we only had to make 3 selections, but ended up with 24 data points. All right, let's go ahead and take a look. For part C, we want the mean, median, and standard deviation. So again, we'll need to pop this stuff into our calculator. So we'll take this data set and we'll just throw this into, say, list 1. So we can go stat and edit, clear out the data from the previous problem and start typing this in. So we've got 310, 325, 335, 340, 360, 365, 370, 370, 410, 410, 415, 420, 420, 420, 430, 430, 440, 440, 440, 450, 455, 470, 485, and then 515. When we're on that 515, since we did type in a lot of data points, it is good to check. It does say L1 of 24 because we had 24 households. Then we can hit stat, calc, and 1var stats, and we can go ahead and get the stuff in here. So our mean in this case would be approximately 409.4, and you can abbreviate that as kilowatt hours, so kWh. The median, if we check that, looks like it should be 420 kilowatt hours. And the standard deviation, which would be approximately, looks like it should be 52.4 kilowatt hours. Okay, when we see this, we notice that the mean is about 409 and the median is about 420. Now, of course, those are not exactly the same. They're off by about 11, but being off by about 11 in the 400s is probably not a big deal. So that probably means that we'd say that the mean and median are roughly the same. And again, we're expecting a symmetric distribution. If we saw visually that it had a large left tail, maybe we could believe that, but that seems very unlikely because, again, 409 and 420, yes, they are different numbers, but they're pretty close to each other given how large these numbers are already. So we're probably expecting something that is pretty symmetric looking, possibly a small left tail. We shall see once we visualize it. So how are we going to visualize it? Well, we're going to try to construct a histogram starting at 300 with class size 25. So we'll do that on the next page, but we'll go ahead and we'll just grab our data set to make that a little bit easier. So we'll copy that and let's give ourselves another page. We'll put our data up at the top here. Oh, we wanted the whole thing. Oops. Let's try that again. Okay, let's grab all of that. I'll do that. Okay, and we'll copy. Perfect. Okay, so let's go ahead and pop that onto the next page here so that we have our data. All right, so this would be, I believe, part D at this point. Yep, we want to construct a histogram starting at 300, class size 25. So we want to do a histogram starting at 300, class size or interval size 25. So we'll need to make a little table here first of the classes and the frequencies. Our first class should start at 300, and since it has a class size of 25, it should go up to 325. Then we should have 325 up to 350, then 350 up to 375, 375 up to 400, 400 up to 425, 425 up to 450, 450 up to 475, and 475 up to 500, and looks like we'll need one more, 500 up to 525. So let's see what we have there in terms of these frequencies. So if we go ahead and take a look at this, 300 to 325, we would just have that 310. So there, and we'll put some separations to help us see that. Then the 325, the 335, and the 340 would all land in here. So we go up to there, so that's going to give us a frequency of 3. Then for 350 to 375, looks like we'd have 1, 2, 3, 4 right there. So we'd have 4. Then for 375 to 400, we actually don't have anything, so we have this weird little gap here. So we've got a 0 there. Then for, and that, sorry, would be, oh, we should have put our line there, and then a line there again. Then for 400 to 425, we'd have 1, 2, 3, 4, 5, 6. So we'd go all the way up to there. So we'd have 6 there. For 425 to 450, the 430, 1, 2, 3, 4, 5. Looks like we'd get those 5 there. So there we go. Keep in mind, right, the 450, for example, would not be counted in this one. It would go into the next one, because remember, we always exclude the right endpoint and include the left one. So then 450, 455, 470, those would all go in our next one. So we've got 3 there. And then this 485 would go in there. So we've got another one. And then the 515 would go in our last one. There we go. We can check 1, 4, 8, 14, 19, 22, 23, 24. So we do have 24 data points, as we know that we were supposed to. So there's our frequencies. We can go ahead and draw this histogram here. So I guess for frequencies, we can say that's 2, 4, and 6. 2, 4, 6, and we can label that as frequency. We'll start the 300 there, and then we'll label by the ends of our interval, 350, 375, 400, 425, 450, 475. We'll need a little bit more, 500, and 525. So we have a frequency of 1, then we have a frequency of 3, then a frequency of 4, then we have a 0 frequency, so that would just be down here. We could, of course, sort of bold a line there. Then a frequency of 6, then a frequency of 5, then a frequency of 3, and then a frequency of 1 and of 1. So it looks a little bit weird because of that, but if we were going to describe it as anything, certainly would still be described as roughly or approximately Bell/normal as its shape. So again, the point of these are to show you guys things that are not perfectly normally distributed, but still see that there's a good level of accuracy with the predictions from the theoretical work that we've done. So this would be a histogram here, this weird sort of little gap, but still probably roughly, if we were going to call it anything, we'd call it approximately Bell/normal. So for part E then, if we go back and look, we're again going to ask ourselves, would it be appropriate to apply the empirical rule? And now that we've confirmed that the shape is approximately Bell/normal, we can answer that very easily. Yes. All right, so we can say yes, we can apply the empirical rule since data is approximately normal. Perfect. Again, if it followed some other shape, left skewed, right skewed, uniform, we would not be able to use the empirical rule. But since we've confirmed using our visual display that it is approximately normal, we are able to use this rule. So for part F then, we'd like to say, where should 98% of the data land? Well, we know that that's going to be within one standard deviation. So 68% of data according to empirical rule. We know that that should be x bar minus s up to x bar plus s. So that would give us one standard deviation from the mean. We can plug in those values. X bar was 409.4 and s was 52.4. So we can plug that in, 409.4 minus 52.4, and then 409.4 plus 52.4. If we evaluate those, again, we can just use our calculator. 409.4 minus 52.4. Low end is 357, and the high end, 409.4 plus 52.4, gives us 461.8. All right, let's use a little visualization there. We'll do that in red. And for G, just as we've sort of been doing on the previous one as well, we'd like to know what percent actually lands in here. So how accurate is this prediction? So let's go ahead and see. So 357 up to 461.8. So 357, oh, we already used red. Let's not do the same. Sorry about that. Let's use a different color. Let's do it this time. Do that in green. So 357 up to 461.8. So 357 would allow us to include here all the way up to 461.8. So 461.8 would get all this stuff there, right? 455 would be in there, but 470 would not. How much data is that? Well, we can just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we got 17 of the data points. Out of how many we had? Well, we had 24. So if we do that, 17 divided by 24, we see that that comes out as approximately, if we write it as a percentage, 70.8%. So notice that even though this guy sort of has this weird gap here, this sort of missing piece in the curve, the accuracy is still very high. Right? We predicted 68% should land there, and we actually found 70.8. So again, pretty accurate considering that this thing is not a perfect bell shape. All right, let's repeat this again for the 98% for H, or for the 95%. So for the 95% of data, according to the empirical rule, well, we should find that in x bar minus 2s to x bar plus 2s. So if we plug that stuff in, we'd get 409.4 minus 2 times 52.4, all the way up to 409.4 plus 2 times 52.4. So if we go ahead and do that, 409.4 minus 2 times 52.4, our low end should be 304.6, and 409.4 plus 2 times 52.4, our high end should be 514.2. All right, so let's go ahead and we'll do this in blue this time. So 304.6, well, that is going to catch everything on that end. 304.6 is definitely lower than 310. And the 514.2, well, it'll just barely miss that 515. So it'll be all the way there. So that 515 is just barely outside the 514.2. So that means that that is going to catch everything except for that one data point. So in terms of the actual percentage here, we would say that that's 23 out of 24. And 23 divided by 24, if we did that, that comes out as about 95.8%. So what should have been 95% of the data actually turned out to be 95.8%. Again, in a really good level of accuracy from a theoretical rule that applies to a perfectly normal distribution to something that is only roughly bell-shaped. All right, so these two examples hopefully justify to you that understanding how to work with normally distributed data, the z-score, table A, the empirical rule, really is meaningful, not just when we assume that we have all this knowledge about the population, but it really does apply to data sets that are also roughly normally distributed. We're going to keep running into things where the normal distribution tells us a bunch of information. So we're going to continue to sort of see this and use this as we move further into inferential statistics. I just really wanted to demonstrate to you guys, though, that even when our data sets only sort of are rough approximations of a bell-shaped curve, these conclusions still show a good level of accuracy. In our next video, we'll be changing gears a little bit and sort of finishing up a few more basic definitions by talking a little bit about statistical biases.